Thanks. We come to the second speaker of the morning session, that's Browne. We will talk about an hour of magic, but you have only 40 minutes for that. Okay.
So thank you very much. So,
that's my show.
So I have a little bit less than an hour to tell you about our recent research, but I'm going to talk about something called magic state distillation, which is it's a component of fault-tolerant quantum computation. So it's sort of an aspect of, I guess, the most state-of-the-art fault-tolerant quantum computing schemes use this as a sort of an intrinsic component. And we've been working on this. These are the two guys who actually did most of this work. This is Hussein, who's my student in UCL, and Earl, who's a postdoc in Jens Isaac's group in Berlin. And magic state distillation was first proposed in a paper in about 2004 by Browne and Kitaev as a really sort of smart way of achieving universality in quantum computation. And to really explain what it is, well, to answer this question. So what can we add to the stabilizer operations to achieve universal quantum computation? But for this question to make any sense, of course, I need to explain what are the stabilizer operations. So the first few slides will just be going through something which some of you will be familiar with, some of you may be less familiar with, but what are the stabilizer operations and what role do they play in quantum computation theory. So the definition seems fairly dry, but it arises very naturally in quantum computation theory. And so it's all about the Pauli group. So the Pauli group are simply the group that you construct by taking Pauli operators, so the classic sigma x, sigma y, sigma z, and the identity operator, and forming tensor products of these. So we say in particular the n-qubit Pauli group consists of all possible n-qubit tensor products. It turns out that the group structure here is extremely useful. So in order to achieve a group here, we allow prefactors plus and minus 1, which arise, if you remember, when you multiply x and z together, you get y with a prefactor of I. So if we put all those prefactors in, we get a group, and this is called the Pauli group. Now the Pauli group then lead naturally to an important class of states called stabilizer states. For example, all of the entangled resource states that Elham spoke about in her talk belong to this family of stabilizer states. And they have a very nice definition in terms of the Pauli group. So they're defined as eigenstates of a particular set of Pauli operators. Now here's a very simple example of a stabilizer state, computational basis state 0 and 1. And state 0 is the unique eigenstate of z with a plus 1 eigenvalue, and state 1 is the unique eigenvalue of minus z, the only eigenstate which has a plus 1 eigenvalue. And in general, if we have an n-qubit state, we find that 2 to the n of the Pauli operators, 2 to the n of the Pauli group operators have this property that they leave the state invariant, i.e. the state is a plus 1 eigenstate. So there's a nice alternative definition that once you've identified these operators which leave the state invariant, you can use those to directly write down the state. And we call these operators stabilizer operators because they leave the state invariant. So for example, z is a stabilizer for 0, minus z is a stabilizer for 1. And when we have an n-qubit state, we find that the stabilizer has, as I said, 2 to the n components, and in fact, because it's composed of commuting Pauli operators, it forms a 2 to the n element abelian subgroup of the Pauli group. And because it's an abelian subgroup, we can describe it just in terms of n generators. So this is very nice. We've seen that entangled states with n particles have a description which scales exponentially in n, but in the stabilizer language, we can completely define the state using just the n generators of the stabilizer group for that state. So these are two very trivial examples, but when we generalize to many qubits, we get important entangled states such as this Bell state, which you see has stabilizers XX, ZZ, and minus YY. And we can choose any two of these operators here to form the generator. Okay. So these generators play a very important role in describing the state. And as I said, there are n of these for any n-qubit stabilizer state. Okay. So in magic state distillation, we're going to be interested in mixed states. So we generalize slightly the definition of stabilizer states to include convex mixtures. That just means we can use a random number generator to prepare these states. With a certain probability, we prepare one of the stabilizer states. And there's a very nice geometric way of understanding qubit states. We can always represent qubit states on the block sphere. And when we do that, we find that there are actually 6 single qubit stabilizer states, basically the plus and minus eigenstates of all of the 3 Pauli operators. And on the block sphere, these sit very nicely at these points which are extreme points of an octahedron. And then the mixed states, which we get by taking convex mixtures, of these states will lie inside or on the surface of this octahedron. Okay, so we can describe them in these ways. And so now we've defined the stabilizer states. This gives us a natural way of defining the stabilizer operations. They're simply operations which map stabilizer states to stabilizer states. So an important component of this are the unitary operators, which map pure stabilizer states to pure stabilizer states. And these are called the Clifford group. And they have the algebraic property that when we transform any Pauli operator by conjugation with one of these unitaries, it's mapped onto a Pauli operator. So that has the consequence that it maps stabilizer states into stabilizer states. We also need to consider measurements. And again, the measurements which will transform stabilizer states to stabilizer states are measurements of the Pauli operators themselves. And because we're including randomness, we can take convex combinations of all of these things. So now the reason why we can even ask the question, what resources do we need to add to this stabilizer operations to get universal quantum computation, is the Gossamer-Nil theorem. And the Gossamer-Nil theorem is a consequence of the efficiency of the description of these states, and that we can also efficiently describe all of the transformations in the stabilizer operations. And it simply tells us that if we have a quantum computation where we only ever have stabilizer states in our quantum computer, we start with the stabilizer state, and then we perform stabilizer operations, this can be efficiently simulated on a classical computer. And you can show that as a computational model, the stabilizer operations are very weak. I mean, you can't even generate a nonlinear gate such as a classical Toffoli gate within this picture. Okay, so there's a nice way of understanding the mathematics of the stabilizer operations in terms of arithmetic modulo 2, so binary arithmetic, and all of these updates correspond with linear updates on binary strings. So we can't achieve nonlinear functions such as the Toffoli gate. So there's the Gossamer-Nil theorem plays a very important role in quantum computation because many of the states which arise in the Gossamer-Nil theorem are very important in quantum computation. So it's natural, just from a theoretical motivation, to ask what's the extra ingredient which we need to add to this already rather rich model of the stabilizer operations, but what's the extra operation or extra ingredient we need to add to get universal quantum computation? So that's a theoretical motivation for this. And one answer to this, which has been known for a very long time, is that we can add either non-Clifford unitaries, or in this example, we can add non-stabilizer states. So we take a pure state which is not one of these 6 stabilizer states, we can actually use it as a resource to generate non-stabilizer operations. And here's a nice circuit which does this. So if we take a state which is an equal superposition of 0, 1 with some phase, just by using a controlled NOT gate and a measurement, we can sort of use this state in combination with some input qubit state and use this resource together with these operations here, which are all stabilizer operations in the middle here. But this non-stabilizer state together with these stabilizer operations gives an effective non-stabilizer operation on this input qubit. And you can show that if you have a supply of pure non-stabilizer states together with stabilizer operations, that's a model for universal quantum computation. Now there's a more practical motivation, and this is fault tolerance, and this was really the inspiration for this work, is that the stabilizer operations tend to arise in most models of fault-tolerant quantum computation. And in particular, the most recent models with high thresholds, such as the model from Manny-Nil and Rausendorf and Harrington's cluster state model, the only logical operations they can achieve sort of natively are stabilizer operations. So we have these models with very high thresholds, so that Rausendorf model has an estimated threshold of around 0.75% error. They have very high thresholds, but natively they can only achieve stabilizer operations. And so they need also this extra ingredient to achieve quantum universality. But because these are fault-tolerant models of computation, they need to be executed in the context of noisy systems. We're trying to realize quantum computation with noisy systems, so we can't imagine that we can perfectly prepare pure non-stabilizer states. So we then have to modify our question slightly and ask what mixed state resources can we add to the stabilizer operations to achieve universal quantum computation. And this would be, so we have our stabilizer operations, which come from our fault-tolerant model, and we'd like to, by adding ancillary states, which are now necessarily mixed states because of all the noise, which of those states can we add to the stabilizer operations to achieve universal quantum computation? And so magic state distillation solves this problem. It's a protocol which, given many copies of a particular family of mixed states, converts them via stabilizer operations alone into a smaller number of copies of nearly pure states which are non-stabilizer states and which you can immediately use as resources for universal quantum computation. So magic state distillation is what makes Robert Rausendorf's scheme and Manny-Nil's scheme universal for quantum computation and hence computationally useful. And so this distillation scheme, we call it distillation, and you'll see why because of this particular structure. It's quite similar in some senses to entanglement distillation. What we do is we take a number of copies of some mixed state, this is going to be our resource state, and then we perform the following steps. Now I'll explain in the next few slides what these steps mean, but we normally apply some twirling, and then we project onto the code space of a stabilizer code. So I'll just explain in the next few slides what those terms mean. Twirling is a very simple idea. It's the averaging of a state over a symmetry group. So, for example, if we take our state, so this dot here represents a state. You can see this is like a slice of the block sphere, so we've got the 0 and 1 state there, and plus and minus states there. So this is our state. Now if we apply a Hadamard to that state, what does the Hadamard do? It actually reflects along this dotted line here. So the Hadamard, maps 0 to plus and plus to 0, so it's this reflection here. So the Hadamard would take the state from here to here. But if we now average the state, and we mix together the state with probability of half we do nothing to the state, but with probability of half we apply the Hadamard, then the convex combination of those two possibilities is this state living in the middle of the line here. So that's an example of twirling. What twirling does is it averages over all elements of a subgroup. Here the Hadamard just generates a two-element subgroup, so it's the identity operator and the Hadamard, but the same trick works for any subgroup. And it essentially projects the state onto the axis of symmetry defined by that subgroup. So here the Hadamard has this axis of symmetry down the middle between 0 and plus, and this Hadamard 12 just projects you onto this symmetry. And this is a nice feature of magic state distillation, that because we can often project states onto an axis of symmetry, we can now study the properties of states in general just by studying states which live along this line. Okay, so we're going to be interested in distilling states, i.e. pushing them up this line to the surface where they're now pure states but not stabilized states.
Then the group should be always the normalizer group to keep it within the same picture, or it
No. So this group, I mean, twirling is defined by a group, and you can define twirling for any group really.
But for the magic state distillation, it will be always a subgroup of
The important thing here is that we're only in our magic state distillation. We're only allowed to use stabilized operations, so we're only allowed to twirl using Clifford group unitaries. So we use Clifford group unitaries and classical randomness to achieve this. Okay, so the second technical element of magic state distillation are stabilizer codes. And stabilizer codes are really the bedrock of quantum error correction theory. If you read chapter 10 of Nielsen and Schwang, you learn everything you need to know about stabilizer codes. And they're very simply constructed. We construct a basis to represent our logical qubits out of stabilizer states. So in particular, we represent k logical qubits over n, where n is greater than k, physical qubits. Here's a very simple example. We can represent the logical state 0 in 2 copies of 0, 0, 0, and logical 1 in 2 copies of 1. And you see that these two states are orthogonal states, which we need to represent these orthogonal states. And orthogonal stabilizer states have this very nice property that their stabilizer generators are always the same up to a phase. So in this case, we see that the generators for the stabilizer group for this state are ZZ and plus ZI, and the generators for this state are ZZ and minus ZI. And this is always true for any 2 orthogonal stabilizer states. So what we do to generate the stabilizer code is we just consider the subspace spanned by these states, and we use that to encode our qubits. And what this gives us is now a stabilizer description for the subspace as a whole. All we need to do is we just retain those members of the stabilizer, those stabilizer generators which are the same for both of these states, and this forms a stabilizer group for the new code space. So stabilizer codes also have this very nice stabilizer description where we can generate a stabilizer group by having just specification for a small number of stabilizer generators. And in particular, if we have k logical qubits encoded in n physical qubits, we end up needing k minus n stabilizer generators. Another really nice feature of the stabilizer formalism for quantum error correction and why it's so important is that it sort of explicitly describes how one then detects errors. Because we know that all the states in the stabilizer code space are +1 eigenstates of every member of the stabilizer group. So we can detect errors by just making measurements which correspond to the operators in the stabilizer group. So for example, to detect an error on this qubit, we measure z tends to z. And the nice thing, because of the group structure, it turns out we don't need to measure all members of this exponentially large stabilizer group. We only need to measure the stabilizer generators. So to perform quantum error correction with a stabilizer code, to detect the errors, all you do is you choose a set of generators for your stabilizer code and measure those operators. So for an example of that, a very famous code is the so-called 5-qubit code, and that has these particular stabilizer generators. Okay? And so in order to detect errors on this code, these are the 4 measurements that you make. Okay, so I've suppressed the tensor product symbol here. So XZZXI means a tensor product of these operators acting on 5 different qubits. And so some of the most famous codes, and ones you'll read about if you open Nielsen and Schwang, are the 5-qubit code and the Steam code. And they also have some very nice error-correcting properties. They work very well as a basis for fault-tolerant quantum computation. Another code which is less well known was actually introduced by Browne and Pitaya for the purposes of magic state distillation. And this is called the quantum Reed-Muller code. And those of you who know about classical coding theory will be familiar with Reed-Muller codes. The quantum Reed-Muller code is literally just the quantum generalization. There's a standard method of transforming classical codes into quantum codes, called the CSS construction. And this Reed-Muller code is obtained just by performing that construction to a classical Reed-Muller code. Okay, I won't go into the technical details of that code, but it's got a lot of very nice properties. Okay, so that means we can go back, having sort of explained those pieces of jargon, we can come back and see that the magic state distillation protocol is very simple. We just take n copies of a state, we perform this twirling on each of the qubits individually. That just simplifies our problem, it pushes all the states onto a line. Then we do one round of error detection using a stabilizer code. So we take these n qubits and we measure the stabilizer generators for a particular code, for example, a 5-qubit code, and we only accept this operation when we detect no errors. If we detect errors, in magic state distillation, we're often not able to correct those errors, so what we do is we throw the state away, and only say our round of distillation was successful when no errors were detected. So mathematically what this does is it projects the state onto the code space of the stabilizer code, but in terms of the implementation, this means that this is a non-deterministic operation. So it only succeeds with a certain probability. So after this, we've now projected our qubits onto a code space, so our qubits are now encoded. What we want to do now is recover a non-encoded qubit, but that's easy to do because for every stabilizer code, you can always decode. So we can always go from this encoding to an unencoded state just by using stabilizer operations. It's a nice property of stabilizer codes. And they're within our lexicon that we're allowed to use in magic state distillation. So we just simply perform that decoding, then we're left with a single copy of a state. So we've gone from n copies of a state to just one copy of a state. And what we want is for distillation to occur, meaning that the state is pushed up towards the pure state boundary here. So this is, again, is the same slice we had before of the block sphere. The first type of magic state distillation which Browne and Kitaev discuss is the H state magic state distillation. So the H state is simply the eigenstate of the Hadamard operator. And as I said, the Hadamard has the action of flipping along this line of symmetry. So that means the pure state, which is an eigenstate of that action, are going to live, the two pure states are going to live up here and down here. Again, the one up here has +1 eigenvalue, so that's the one we'll consider. This magic state distillation protocol works by using Hadamard twirling to transform any state over here onto this line. And Browne and Kitaev showed that provided the noise on the state is below a certain threshold, I mean, provided the state lives on this line between the pure states and this red boundary, then we're able to distill this state, meaning that repeated iteration of the protocol I just gave you moves the state closer and closer and asymptotically reaches the pure states here. A little word on how we describe the noise thresholds for these protocols. You can see that there's this red line here is very important. If we start with the state below this red line, the distillation protocol fails. And in fact, we'd expect the distillation protocol not to work anything in this shaded region here. So this shaded region you can see is the convex hull of these four stabilizer states. So that means everything inside the stabilizer region is a mixed stabilizer state. And we know that we can't achieve universal quantum computation by stabilizer operations on stabilizer states. So magic state distillation must fail for any state living inside this octahedron. So we know that we can't achieve distillation for anything in this region. And Browne and Kitaev showed that for most of this region outside of this octahedron, you can actually achieve distillation. So at least on this plane here, they achieved a threshold very close to this line. And the way to understand these thresholds, there are different ways of quantifying it, but one way of thinking about it, if I start with a pure state on the boundary here, and I apply depolarizing noise just means taking the state and making a convex combination with the maximum mixed state, and the effect of that just pushes you straight down the line between this pure state and the point at the center of the state space. The the centre of the state space is always this maximum mixed state. Okay, so our noise pushes us down here. And we can then write this process in terms of the parameter epsilon, which basically tells us how far away we're on this, how far along this line we are. So if epsilon is equal to 0, so I've got my axes the wrong way, my axis label's the wrong way around here. But if epsilon is 0, we have 0 noise, and we're up here on this line. If epsilon is 1, we have maximum noise, and we're down here. So the error threshold in Browne and Kitaev scheme is 28.1%. So that means coming down this line between here and here, 28.1%. You see it's very close to this threshold here. So that was their initial proposal, and it's a very important result because it tells you that if you can build fault-tolerant stabilizer operations, then basically there are many noisy states which you can use to achieve universal quantum computation. Now, this work was then improved in the same year by Ben Reichard, who showed that by modifying the protocol slightly, so instead of using the 15-qubit Reed-Muller code, which Browne and Kitaev used, if instead of that you used steam code, 7-qubit code, you actually achieve a threshold which is tight against the stabilizer boundary. So everything above this line can be distilled. Okay. And this is just one slice of the block sphere. Browne and Kitaev also identified another magic state called the T state. The T state is another eigenstate of the Clifford operation. And just as the Hadamard you can think of as a reflecting, it's a symmetry transformation on the octahedron, which just reflects along an edge. If you do a rotation around the centre of the face of the octahedron, that's another symmetry operation. And we call this unitary the T operation, and its eigenstates simply live on this axis, living in the middle of the, this triangular face of the octahedron. So the T states live on the surface here. Browne and Kitaev showed that T states could be distilled using the 5-qubit code, and there they got a noise threshold of 34%. So that's a pretty high amount of noise that can be tolerated here. But it's quite far away from the stabilizer region threshold, which is at 42%. So between them, between Browne and Kitaev's work and Reichard's work, we see that most non-stabilizer states are distillable. So most states living outside this octahedron are resources which you can use to achieve universal quantum computation. And that was a very nice result. And it just left a small open question of what about this small gap between the threshold of Browne and Kitaev's T magic state code and the stabilizer region. So we investigated this and we were wondering, can we close this gap? And in fact, in some work that Earl Campbell and I did a few years ago, we were able to show that no, you can't close this gap. In fact, there's always a finite region of states which cannot be distilled by any code. We gave these states the name bound states in analogy to bound states in entanglement distillation. So I mentioned that just tangentially because this will come up when we go to more recent work which is based on qubits. So everything I've talked to you about so far is work, mainly work from 2004. So what's new this year? Well, this year really, quite a few people have started to becoming interested in generalizing fault-tolerant constructions from qubits to QDIDs. There are a number of reasons for that, which I'll explain in a few slides. But basically, the main change is that our individual data carriers are going from qubits, 2-level systems, to d-dimensional systems. Okay. So what changed? D-dimensional systems, we can represent states just the same as qubits. We can also generalize the Pauli group in a very simple way. So the X operator, which previously flipped you between 0 and 1, now cycles you around, takes you from state J to state J plus 1. So cycles you around this group modulo D. And what does Z do? Z for qubits puts a phase on your qubit state. And again, this Pauli Z also puts a phase. Now the phase is the dth root of unity. But that's the only difference. So, and some people call this the Heisenberg-Weil group. I think you may hear about this in other talks this week. But basically, once you do this generalization, apart from a few little technical subtleties, all of the stabilizer construction goes through. So everything everything that I told you about qubit stabilizer states you can generalize more or less to qubit stabilizer states. And the main difference is whereas the qubit stabilizer formalism is really based in addition modulo 2, now we work in arithmetic addition modulo d. So in order to achieve this, we need to work with a field, and it's convenient to only consider d such that d is an odd prime, because then the natural sort of arithmetic that you choose, modulo d, is a field and everything's well behaved and everything generalizes very nicely from the qubit case. So in all of the rest of this talk, I'm going to assume that d is always an odd prime, but apart from that, d could be any number at all. So why would we care about this? Well, one motivation is that it might be useful. Lot is known about thresholds for fault tolerance for qubits, but we don't know so much about fault tolerance with qubits, and maybe there could be an improvement there. Maybe in thresholds, but maybe also in terms of efficiency in reducing overheads. And also there's a sort of a theoretical reason which makes this very interesting to study, is that the state space for qubits is very, very different to qubits. Now, I've told you that many of the formalisms we use to study qubits map across very straightforwardly, but one thing which doesn't is the Bloch sphere. So the Bloch sphere is beautiful. We have this beautiful, nice sphere representing our pure single qubit states. We have this lovely octahedron. It's very sort of simple, symmetric, and easy to understand. The qubit state space for d greater than 3, however, is not a hypersphere. We have to throw this Bloch sphere picture out the window, and we get all sorts of new features. In particular, the boundary of the state space is no longer solely inhabited by pure states. So we have states on the boundary of the state space which are mixed states, so the mixtures of these pure states here and here. But if we try and move away from the centre of the state space, remember I said the centre of the state space was always the maximally mixed state, which is the identity operator. So if we start with a state here and we subtract identity from it, normally subtracting identity from any state of qubits pushes you out towards the pure states. But if you do that here, what you find is that at some point you no longer have a positive state, and so you actually run out of, your positivity condition breaks before you reach the surface of the hypersphere. So for that reason, the qubit state space is rather more complicated than the qubit case, and you know, you might even think, will magic state distillation work at all? Because so much of the underlying theory of the magic state distillation protocols uses this beautiful symmetry of the Bloch sphere. And here's another motivation to study this. This is very recent work by Howard and Wim van Dam, and they've shown that the non-stabilizer region for qubits is much, much bigger than the non-stabilizer region for qubits. So the non-stabilizer region for qubits was this little slither between the surface of this octahedron and the surface of the sphere. If you consider qubits, however, you can always find surface pure states which are very, very far away from the stabilizer region. And they can tolerate noise rate, depolarizing noise of d over d plus 1, which is a very high number, in order to map them down to the stabilizer region. So the non-stabilizer region is much bigger, and this gives us some grounds to think that there could be some more inherent robustness here against error. Okay, so I'll speed up a little bit, but I'll just mention quickly some very recent work from just a few weeks ago. I won't go through the technical details here, but what these people have shown is that you get bound states for magic state distillation, also for qubits. And the reason for that is there's something called the Wigner function, which is a function you can use to, it's like a phase-based function you can use to describe qubits. And it's a function which takes d by d real values. It turns out for pure states, if its Wigner function is non-negative, it's a stabilizer state. But the converse is, the same thing does not hold for mixed states. And it turns out that if you have a mixed state, which has a non-negative Wigner function, it's a bound state for magic state distillation. You cannot distill it. This is very nice recent work from this group Weich in Waterloo. Okay, so that tells us that magic state distillation was impossible for certain qubit states. Weirdly, when this paper came out, there are actually no papers in the literature showing that magic state distillation was even possible for qubits. But we were sort of working on this in parallel, And we actually were able to show that yes, magic state distillation does work for qubits. So I'll just give you, in the sort of 5 minutes I've got left, just a quick overview of our results. If you want any of the technical details, just come and talk to me. So we took two approaches, really. The numeric approach, which is let's just throw some numbers at this, do some calculations, and see if a naive generalization of the magic state distillation protocol works. And we found it does work. So that was very nice, and that was this first paper on the subject. But we're more interested really in understanding the underlying theory, so we want to have an analytic approach. And so more recently, in work that's not yet on the archive but will be soon, we're able to show some very general classes of magic state distillation which work for any dimension. Okay. So the numerical approach, we just had to take an example, try it, and of course that doesn't tell you anything about higher dimensions. So this was the first example we looked at, and it was for Q-trits, and we found that the eigenstates of the Q-trit Hadamard gate, which is this discrete Fourier transform here, if we consider the convex hull of the three eigenstates of this operator, which I'll label with the eigenvalues plus, minus and I, then this forms a little slice through the qubit space. Okay, a little triangular convex hull of these 3 points. And we studied magic state distillation for this plane, this slice of states. And what we found was that we can map out this slice, and we can find the stabilizer states, which is this red region here. We can find the non-negative Wigner function states, that's this yellow region here. And so starting with states on this plane, we constructed some magic state distillation protocols and saw how well they worked. And we found that 2 of them are indeed magic states, 2 of them can be distilled. And what we used was a combination of the 5 Q-trit code and the steam code. These are both very natural generalizations from the cubic codes to the qubit case. And we found that they worked. And so just to give you a map of our results, this is this plane that we saw here. So these regions here are non-distillable because they're all positive Wigner function. It turns out for these corners here, the corners near the H plus and H minus states, all of these states here are distillable. So we get the same tight threshold that we had for qubits. So all of these things can be distilled. But in this region here, and this was the region that Van Dam and Howard discovered, this is this huge region, this huge gap between the pure state and the stabilizer region. In this region, the distillation protocols didn't work at all. In fact, all of our distillation protocols just took a state here and dragged it to the identity. So we have this sort of interesting contrasting behavior here. For these 2 eigenstates of Hadamard, we get distillation just like in the cubic case, but for this other one, and this potentially more interesting one, it doesn't work at all. And we also found another magic state, which I call the question mark state, because we don't really understand where it comes from. This is what it looks like, but we don't yet have the underlying theory to explain why this is a magic state, or indeed where these parameters come from. That's something we're working on. But this also distills and has a threshold of 34%. So these have got good noise thresholds. And this sort of summarizes our results. You can see that the 2 of these states that we've identified have thresholds which are as good and in fact slightly higher than the cubic case. Now, before I finish, just to summarize our analytic work, which is very new, it's not been put on the archive yet. What we did was we went back to Reed-Muller codes. And Reed-Muller codes are very nice because they have a lot of structure, and it's that structure which is the basis for Browne-Kataev's protocol. And in particular, they have this very special property that they have a non-Clifford gate which is transversal. Now what that means, what transversality means, is if you want to apply a gate U to your logical encoded qubit, we say that implementation is transversal if the way we do it is by applying a tensor product of U's to all the individual qubits. And this is very important in fault tolerance because if you can apply your unitaries bit by bit, then errors don't spread throughout from one bit to the next. So it's a good way of sort of isolating your errors. But it also is useful just for its analytic properties. And it turns out that the transversality of a non-Clifford gate is at the heart of Browne-Kataev's Reed-Muller distillation code protocol. So that's what we've been able to generalize. And in fact, we've been able to show that by generalizing this construction to qubits, in every prime dimension, we can find Reed-Muller codes with this non-Clifford gate transversality, and that leads directly to magic state distillation protocols. And these magic state distillation protocols really have a very nice, simple structure. We can analyse them analytically and prove that in all dimensions, or prime dimensions, we do get a finite noise threshold. And so we're able to show that magic state distillation does actually work for any prime distillate, for any prime dimension. So to conclude, I gave you an introduction to magic state distillation, and I told you about the most recent work in this area, which is to generalise to QDITs. And the bottom line is that it works. Magic state distillation does generalise to QDITs, and the thresholds, at least for the Q-ship case, are slightly better than in the cubic case. We don't yet have any analytics on how the thresholds scale as D gets bigger. And indeed, there are a number of other open questions that we want to explore. We still have these pesky, very robust Howard Van Dam states, which we don't know how to distill, even though, in some sense, these look like these should have the best performance. We're also interested in the computational complexity of simulating magic state distillation when you consider, when you start bound non-distillable states. And more beyond the general and analytical work we want to do, we're really interested now in the implications for fault-tolerant computing, because what this means is, because magic state distillation works in higher dimensions, we can generalise Rouse and Dorf's scheme to higher dimensions, and who knows, we might find a higher threshold. I mean, there are reasons to think you might get a worse threshold, but there are also other reasons to think you might get a higher threshold. Why not? Let's see what we get. Okay, so these are some references. Thanks very much for listening.
Thank you, Dan. Other questions? Sure.
Could you say how you compute the noise threshold briefly?
Yes, the way we do it is numerics. So these are numerical estimates of the noise threshold, and it's literally we take a state and we apply the distillation protocol numerically, and we track its convergence. So it's similar to how you find thresholds in fault-tolerant quantum computing. You sort of look for the break-even point, and you look for the point where the distillation no longer takes you to the surface, but takes you away from the surface. But more formally, these are numerical upper bounds to the threshold, rather than precise statements of the threshold.
Okay, are there more questions? Sure.
I'd like to ask perhaps a stupid question from the point of view of an experimentalist. You motivated magic state distillation as a mean of making a non-Clifford or non-stabilizer state, right?
Yes.
Using only, Clifford group operations, I
Yes.
suppose. But it seemed to me the act of twirling around the Hadamard, your example, would require a non-Clifford gate.
No. So
That's maybe where
the twirling is an averaging using a Clifford gate. So the way you twirl with the Hadamard, it uses Clifford gates and a random number generator. So you use a random number generator with probability a half, you do nothing, probability a half, you apply a Hadamard. And in fact, so we use twirling. Twirling is it's a theoretical tool to simplify the problem. Normally you don't need to use it. I mean, that seems like a crazy thing to do, adding more randomness to the protocol. And in most of these cases, you can actually remove the twirling. But in principle, twirling you apply it, you implement it with Clifford group operation and randomness. But it's more, we use it more as a theoretical tool rather than something you would, in any implementation of this, you'd figure out a way to avoid the twirling. Because these are more sort of proofs in principle. As you try so another thing we're doing, an open thing we're working on here, is to improve the efficiency of these protocols. And Browne and Kitaev weren't really interested in optimizing that at all. When you start thinking about improving the efficiency of the protocols, reducing the number of copies you need, really optimizing things like that, you can make substantial improvements. And we have some other results where we've been able to increase or reduce the overhead needed quite significantly. And taking out the twirling is one of the things you do. So it's a sort of a theoretical, useful tool, rather than something you would actually do in the lab. And the key lab thing to do is the measurement of the stabilizer generators. That's the most important sort of physical thing that you do in this approach.
Good. Last call for questions. Okay, if there are none, then thanks.